Electrical transportation represents a paradigm shift in the way we power and propel vehicles, encompassing a diverse range of modes such as electric cars, buses, trains, and even bicycles. At its core, this approach leverages electric power stored in advanced batteries or supplied through overhead lines to drive the wheels or propulsion system of these vehicles. Electrical transportation involves the use of electric power to propel vehicles, reducing reliance on traditional internal combustion engines. This transformation is closely tied to principles of electricity and magnetism. Electric vehicles rely on batteries to store electrical energy, and these batteries use electrochemical reaction based on principles of electricity. Moreover, the electric motors fundamental to electric vehicles propulsion operate on the interaction between electric currents and magnetic fields, a concept rooted in electromagnetism. Thus, the synergy between electricity and magnetism is pivotal in driving advancements in electrical transportation. Now, let's move for the significance of electrical transportation. The first one is environmental impact. One of the most significant is its positive impact on the environment. Electric vehicles produce zero tailpipe emissions, contributing to the reduction of air pollution and mitigating the environmental impact of transportation on climate change. Next is energy efficiency. Electrical transportation can be more energy efficient than internal combustion engines. Electric motors are inherently more efficient in converting stored energy into movement, leading to potential energy savings and reduced overall energy consumption in transportation. The last one is economic opportunities. By shifting away from traditional fuel sources, electrical transportation helps decrease dependence on finite fossil fuel, contributing to energy security and reducing the environmental impact of extracting and burning these resources.
Okay, next, we go to electricity and magnetism in electric transport. There are a lot of components of electric vehicles, but I want to talk about the main ones. First, the batteries. Batteries as energy storage systems, which are essential for all electric vehicles. There are hundreds of individual cells packed into modules of pockets to make one large battery. They say the capacity of a battery pack influences the vehicle's range, so that means the larger the battery, the farther a car can go on a single charge. When charging, the cable coils receives alternating current, AC power. They occur changing magnetic field, inducing an electric current in the coil, which then charges the battery. Then, electric motor operation. An electric motor that is supplied by battery energy runs electric vehicles. So, it converts electrical energy into mechanical energy. A rotating component of the motor, which is the rotor, is turned by a magnetic field created when electricity from the battery is sent to the stator, which is a stationary part of the motor. Lastly, regenerative braking. Regenerative braking is the process by which an electric car uses its momentum to generate energy when the driver applies the brakes. So without wasting any energy, the electricity is returned back to the battery, so this procedure enhances energy efficiency generally. Okay then, let's move for detailed explanation about electric transport. I would like to give example of electric cars. So how the electric cars work? Basically, they are just similar to regular gas-burning vehicles, since they both do have an accelerator pedal, a brake, and as long as you know how to drive a car, it will be moving. But to make a difference, internal combustion engine (ICE) vehicle gets its energy from a fuel tank of diesel, while the electric cars have the battery cells to store energy. So, most of electric cars typically use lithium-ion batteries, which can shuttle lithium ions between the electrodes. As we know, lithium-ion batteries are common and used in most portable electronics such as cell phones and computers. This is because there are many advantages of lithium-ion batteries like high power to weight ratio, high energy efficiency, good high temperature, and compared to other batteries, lithium-ion batteries have a lower self-discharge rate, which implies they can hold a full charge for a extended period of time. Next, for electric motor, the inverter converts direct current DC power from the battery into alternating current AC power to control the motor's speed and torque, which affects how quickly the car accelerates. So that means electric motors require AC power to spin the rotor that sits inside the stator using the wonders of magnetism, which it runs on a cycle of continuously switching north and south poles, means able to produce a rotating magnetic field which causes the rotor to rotate along with it. Lastly, regenerative braking system that when a driver releases the accelerator pedal, the motor no longer receives power from the battery. So, when there's no flow of electricity from the battery, the motor turns into a generator, transferring the kinetic energy of the rotating rotor back into the battery as storage.
Hi, my name is Nurshasha Nasrin and I'm going to tell you about electrical transportation. In the realm of electrical transportation, physics play a crucial role in various real-world implementation. For instance, physics is fundamental in the development of electrical vehicle (EVs), the design of charging infrastructure, the implementation of regenerative braking system, and the optimization of power electronics. This will enhance the efficiency, performance, and overall functionality of this essential component in the world of electrical transportation. For electrical vehicles that are powered by electricity instead of traditional fossil fuel and use electrical motor and rechargeable batteries. Then, charging infrastructure refer to network of charging station. This can ensure safety and efficient charging processes. Regenerative braking is a technology used in electronic vehicles to recover and convert kinetic energy during braking into electrical energy. This energy then stored in vehicle battery for later use to increasing overall energy efficiency. Lastly, for power electronic, these play a vital role in the efficient conversion of electrical energy in electric vehicle. Interval and converter control and manage the flow of electricity between different components of the vehicle system. Power electronic contribute to the overall performance, efficiency, and reliability of electronic vehicle. Let's talk about the potential benefit and challenges of physics in the realm of electrical transportation. Benefit in the development of electrical vehicle (EVs), which can help us reduce our reliance on fossil fuels and decrease carbon emission. It also allows for the optimization of battery system and electric motors, leading to improved energy efficiency and longer driving ranges. It also guides the design of charging infrastructure, ensuring safe and efficient charging processes for EVs. In the field of electrical transportation, there are challenges related to developing high capacity and long-lasting batteries that can provide sufficient energy for extended driving distances, and overcoming the limitation of electromotors, such as torque and power output, to advancement in physics-based engineering and design. It also striking a balance between the demand for fast charging and the strain it may put on the electrical grid, while also promoting the use of sustainable energy sources. Comes to future development and innovation for electrical transportation, there are some exciting things happen. An advanced energy storage system store energy for later use, providing a reliable and efficient way to manage and distribute electricity. Wireless charging is a method of charging devices without the need for cord or plugs. It uses electromagnetic field to transfer energy from a charging pad to the device. Autonomous driving refers to the ability of a vehicle to operate and navigate without human intervention. It uses various sensors, camera, and algorithms to perceive the environment and make decisions on steering, acceleration, and braking. By using advanced materials like carbon fiber, composite, and aluminium alloy, vehicles can become lighter, improving energy efficiency and increasing driving range. To integrate electric vehicle with the power of grid, bidirectional energy flow, where a vehicle can not only draw power from the grid but also supply excess energy back to it. This concept, known as vehicle-to-grid integration, can help balance energy demands and reduce strain on the grid.
In conclusion, the intersection of electricity and magnetism in the realm of electrical transportation showcase the transformative potential of electromagnetic principles. Electric vehicles leverage this principle through technologies like electric motors, which convert electrical energy into mechanical motion. The symbiotic relationship between electric and magnetic fields, as exemplified in electromagnetic induction for charging, underpins the efficiency and functionality of electric transportation. As advancement continue in both electromagnetism and electric vehicle technologies, the future holds promise for more sustainable and magnetic-driven mobility solutions.